Hi everyone, this is the last video of TOC. In this video I will tell what I covered in 5 modules and what you need to cover extra, and for passing mark what you need to study. Okay. For definition, first in the module 1 you need to study what is DFA and what is NFA. Okay. Next what is epsilon NFA. In module 2 what is regular expression and define pumping lemma and what, that's all. In module 3 define CFG and define LFD, LMD, leftmost derivation, RMD and parse tree, and what is ambiguous, unambiguous, inherit grammar. Next what is PDA, define PDA, and in module 4 that is here define CNF, and they removed GNF but they asked in both of the module paper what is GNF and problem related to that, and in the module 5 you define a Turing machine. Okay. And the closure property of a regular language and closure property of a CFL I not covered in module wise playlist video, but I will cover in this video. And for the passing mark, first you need to study Turing machine construction. Okay. First cover these questions 0 power n, 1 power n, they also it may be a power n, b power n, and this one also. After that the palindrome one they may ask that also. First learn those 3 questions. Okay. This the mark will be vary because in the first paper the Turing machine they asked for 6 marks. Okay, here they asked 6 marks, and here also they asked 6 marks, but in the new paper for the same question they given 10 marks. So first study Turing machine construction and watch module 5 video. Okay, in this video I am not going doing this. Next minimization of DFA. For minimizing the DFA in the both paper they asked the same question, so that is this one. Okay, this one, and here also the question is the same. Okay, so study star D first. Okay, in minimization of DFA basically 3 questions only there. So first the final stage is star D na. You need to learn first, and to get more confidence try these 2. Okay, in these 3 only they may ask minimizing the DFA, minimization of DFA. Okay, next conversion of a CNF, this is pretty easy, you can solve easily. Okay, and push down automata for language one paper asked, and for grammar, and that too mainly they ask this type W reverse and a power n, b power n, that type for language, and they may ask grammar for also. So learn the push down automata and NFA to DFA conversion. So if you know the subset construction and lazy method, they may ask particularly lazy method or subset also. If they not given anything, just they say convert NFA to DFA, then go for lazy method. And for this, if you know the method and they given any question, you can easily solve. Okay, and this one is pretty important. And pumping lemma theorem, that also easiest one, you can study easily, and write LMD, RMD and parse tree. So here you can easily pass. Okay, so first study these topics. Next solve the model paper. Okay, that is the effect of 24-25, and 1A question define DFA to accept strings of A's and B's where language they given. Okay, the input is A and B and the language is this. So you can clearly see from mod K counter problem module 1 they asking this. So to solve mod K counter problem, one question is that equal number of A, equal number of B is odd number of A, odd number of B, even number of A, even number of B. That is the important under mod K, one type of question. Other than that they ask this type. Okay, to solve this we follow 3 steps. That is in the first step we check how many status are there, and in the second step what is the start and the final state, and finally we write the diagram. So this is the question I solved while doing that type questions. Okay, so here they changed number to mod 5, here 3 is there, and 4 I solved 2, and the condition is greater than equal to, here condition is only equal. Okay, first in the beginning you need to know how many states are there. So for mod 5, all possible remainder states of 5 is 0, 1, 2, 3, 4, and all possible state for 4 is 0, 1, 2, 3. Okay. Next, for 3 it is 0, 1, 2, and for 2 it is 0, 1. For naming convenient, I will add Q for this. Okay, and for this I will add P0, P1, P2 and P3. Then start and end state. So all possible combination. Before that, for this all possible combination is a 6 state, 3 into 2. For this 5 into 4, 20 states are there. Okay, that is Q0 P0 and Q0 P1, Q0 P2. So these are the 20 states that are possible, and after that start state is this, and what is the final state? Equal. Okay, they given equal means check here 0 is equal to 0, it is the final state. Then q1 equal to, here 1 equal to 1, na? This is final. Then next 2 equal to 2, next this is the final. After that here 3 equal to 3. 4 final states are there. Next step, we need to construct the DFA. I will erase this. In the step 3, first starting state is Q0, P0. Okay. From there, we need to add one AB. Okay, we are doing what? Adding one A or B. To do that, here this is Q0, P0, right? We are adding one, and check 1 mod 5 and 1 mod 4. 1 mod 5 means here it is Q1. 1 mod 5 is 1 and 1 mod 4 is also 1, and this is P1. So the next state is Q1 P1. Okay. Next, from here I am adding another A and B. So that is add one more to this. 1 plus 1, 2 mod 5. Next 2 mod 4. Q2 P2. Next state is Q2 P2. From there add 1. How much we need to add? We need to complete 20 states. Next 3 mod 5, 3 mod 4, that is Q3 and P3. After that one more, 4 mod 5. 4 mod 5 means 4, right? Q4, and 4 mod 4 means 0, correct? P0, that is Q4 P0. And after that here 5 mod 5 means Q0, and 4 is completed. 4 mod 4, you need to go for again start to repeat, as here is the 0 state. Okay, we need to add here means 0 plus 1 is 1. 1 mod 4. P1, Q0 P1. So continue the loop like this. So this is the final DFA, which looks like this, and so in between you need to write the input is AB. At each stage we are incrementing AB, and what is the final state? This is Q0 P0 is a final state. 0 equal to 0, 1 equal to 1 is a final state, 2 equal to 2 is a final state, next 3 equal to 3 final state, and is there any? No, only 4 final state. So this is the solution. Okay. And one more thing I need to say, in mod k counter problem I solved this question, okay, where I taken there Q0 P0, but here A0 B0 is there. So how to recognize the type of the question? So here they given a mod, okay, mod for W and mod for here also. But in this type of question they asking number of A and number of B's, okay. If I am here in the start state A not B not, then if A comes then I need to increment A only, okay. If a B comes then I will go into increment this B not, okay. So that's why here we are moving A and B in a different path. But in this type of question what we need to do, we are moving A and B together, okay. So this is the small thing I need to tell. And other than that we can solve any mod k counter problem, okay. And they can may ask either from mod k problem or divisible by k problem. In divisible by k problem there is also they given 3, okay, divisible by 3, and only 3 problems are there. So divisible by 4, divisible by 5, so check that one also. So in mod 1 mod k counter problem and divisible by k problem. Next question, this one, write DFA which start with 0 1 or starting with 1 0. So I am starting from here. I need to start with what? 0 and 1, okay. After that I need to accept that string. Next either starting with 1 0 1 0, I need to accept that too, okay. Then what is DFA? DFA means for every state all possible input. Here they given input is zeros and ones, okay. The path to this must be defined. For Q0 0 1 is defined, and here Q3 0 is defined, but 1 from if 1 comes here then it starting with 1 1 0 happens, okay. If I given a self loop, so where 1 need to go, I am creating another state. So Q5 this is the dead state, okay. If 1 comes reject that, okay. For here 1 0, okay, here 0 1 is done, and for this after starting with 1 0 any zeros and ones you can any zeros and ones you will accept this. Next here also 0 and 1 in the middle 1 comes, then here 1, okay, here 1 is done, here 0 comes, then it becomes starting with 0 0 1 happens na. So here add 0 to dead state 0 1. Next here also any number of zeros and ones, and here also any number of zeros and ones. Check starting with here 0 1 1, whether this need to accept 0. Next 1, next any number of 1 this DFA is accepting. Next starting with 1 0 1, here starting with 1 0 any number of 1 accepting here. And what about 1 1 0, starting with 1 1 happens here, so it need to reject, right, according to the condition. Let's check this 1, and if 1 comes again it goes to dead state. DFA is defining that too. And 0 0 1, consider this is need to reject now, so 0 and again 0 comes, it will reject these strings, okay. This is the answer, and you can change this also, because after 1 0 you can create one accepting state only. You can add, you can 1 0 and you can just add this here, okay. You can define this way or you can write that way also. So next question is convert the following NFA to DFA. So they didn't ask subset or lazy evaluation method. So we are lazy now, we are going for lazy evaluation method. So first step, write the starting state, and in the second step write whatever the input are there, And in the third step, NFA transition table. NFA transition table is nothing but see and write here. Transition, how many states are there? 3 states, Q0, Q1, Q2. Right here, Q0, Q1, Q2. Start state, Q0. Final state, Q2. Next, input for 0. If I am giving a 0 here, I am reaching Q0 itself, Q0. 1 comes to Q0 and goes to Q1 also, Q0, Q1. And Q1 here, 0 going to Q2 and 1 also going to Q2. Next to Q2, there is no transition, this is null. Next to DFA transition table, this is important, okay. If a subset construction method, then we write all possible state of Q0, Q1, Q2 we write, and after that we are subsetting that Q0 to Q1, Q0 to Q2, again Q1, Q2 and Q0, Q1, Q2 in that way. But in lazy evaluation method, we only check this side. Whatever new state we are getting, we write here, okay. First stage write that way only, Q0, 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 Q1, okay. After that Q0 here only defined. Next is a Q0, Q1 state is there, okay. Right here, Q0, Q1. Q0, Q1 upon 0 goes to Q0, Q2. Q0, Q2. Upon 1, Q0, Q1, Q2. Q0, Q1, Q2. Check this side for a new state. Q0, Q2. This is the new state. This also new state. Next write Q0, Q2. Q0 and Q2. For input it Q0 and null. And for 1 it is Q0, Q1 and null. Q0, Q1. Check for new state. Q0 already done. Q0, Q1 already done. And this is not done. Q0, Q1, Q2. Upon 0 this goes to Q0, Q2 and null. That is Q0, Q2. And Q0, Q1, Q2 here. Q0, Q1, Q2 here, okay. Next final state, wherever Q2 is there, that is our final state. And check once Q0 is defined here, Q0, Q1 we write here, and don't write any circles and all, only check, okay. Q0, Q2 this also there, and Q0, Q1, Q2 also there, and Q0 also there, Q0, Q1 also there, Q0, Q2 is also there, Q0, Q1, Q2 is also there. For all state we write this side, you need to have a transition. This is only lazy evaluation method. Then after that we need to write a diagram. So starting from Q0, upon 0 it goes to Q0 itself, and upon 1 it goes to Q0, Q1. Next Q0, Q1 upon 0 it goes to Q0, Q2, and upon 1 it goes to Q0, Q1, Q2. So yeah, Q0, Q1, Q2. Next come here, Q0, Q2. On 0 it goes to Q0, and on 1 it goes to Q0, Q1. Next Q0, Q1, Q2. On 0 it goes to Q0, Q2, and 1 it goes to self loop. Next final state is Q0, Q2 and Q0, Q1, Q2, okay. Next one, 2a, find the enclosure of all the state and convert the following NFA to DFA. So this question from epsilon NFA to DFA. So to solve this type of problem, I told there is a 5 steps we need to follow. First one, we need to find enclosure of all state. Then what is the initial state? Next one is write the NFA transition table, and next step DFA transition table, and finally we need to write DFA, okay. First write enclosure of all state. So I am writing here only, okay. So for all state, first we need to write enclosure, okay. So what you mean by enclosure? Enclosure is nothing but a state which is closed first its stage only, then wherever epsilon is moved and reached a state, that also e-close of that state. For example, q naught, first e-close of q naught is q naught itself, then check wherever epsilon goes. Okay, from here epsilon goes to q1 state. Okay, write the q1. After that here it goes to q2 state also, write that also. Next from here q4 also, so q4 also. Okay, next another epsilon goes to q7, right? q7. So these are the e-close of q naught. In the same way we can do for all the states. Next for q1, q1 itself, after that q2 and q4, q2 and q4. Next for q2, q2 here q2 itself, after that there is a no epsilon transition. Okay, next for q3, here it goes to q3 itself, next it goes to q6, from q6 epsilon goes to q1. Okay, and from q6 also it goes to q7. Okay, is there any? So from q3 itself, after that it goes to q6 goes to q1 and also q7. Here q7 and there, and here q1 again goes to q2 q4, right? We need to write q1 q7 q2 q4. Okay, next q4, for q4 there is q4 itself and no epsilon. Next for q5 itself, next q6 goes to q1 and also it goes to q7, and here q1 goes to q2 q4. Next q6 itself, after that epsilon goes to q1 and from q1 again q2 q4 and also it goes to q7. Next for q7 itself epsilon goes no. Next for q8 and for q9 also q9. Next qf itself. Okay, this is the e-closure of all state. Next step, this is the step 1. In the step 2 we need to do what? The start state. Initial, I will write here start state of DFA is e-close of q naught. Okay, e-close of, this is our start state, q naught, q1, q2, q4, q7. Next in the step 3 we need to write a NFA transition table. NFA transition table means check this diagram and write A and B where it goes. For q naught there is no AB transition, so for q2 here there is a transition, and for q4 here B goes to q5. In the same way complete this table. In the next step we need to write a DFA transition table, so I require more space. To write a DFA transition table I need this step only, so I erase all and I will keep it aside. Okay. And for DFA transition table, first write the initial state, that is q0, q1, q2, q4, q7. Okay, and input we have A and B. For A we need to check transition of NFA, that is from NFA transition table. Okay, here A, how many state we need to check? q0, no. Next to q1, no. Next to q2 there is a NFA goes to q3. Next to q4 no. Next to q7 is a q8. In the same way check for B also. Okay, q0 no, q1 no. Next to q2 null. Next to q3 is not there, and for q4 q5 is there. Okay. Next Q7, for Q7 null. This step is complete. After that find E close of Q3 and Q8. E close of Q3 is, write this, Q3 6 7 1 2 4. After that Q8, E close of Q8, E close of Q5, Q6, Q1, Q7, Q2, Q4. Next we need to write state for all the E close. Okay, I will take this one. After that Q5, Q6, Q1, Q7, Q2, Q4. Input A, input B. Check Q5 is null. After that Q6 no. Next Q1 no. Next Q7 is Q8. Next Q2, Q4 are there, that is Q3 and null, Q3. Next check for Q4 is there, then Q5. Next Q8 is there, no. Okay, next write E close of Q8 and Q3. Similar, this one only, Q3. So same, and we done with this here. And another state is there, we need to write in the state. Okay, write Q3 6 Q7 Q1, next Q2 Q4 Q8, write together. Then use these flower braces and all, A and B. Okay, next check here, Q2 and Q7, Q2 and Q7 is there, so Q3 Q8 is there. And here for B, Q4 and Q8 required, Q4 Q8, so it is Q5 and Q9. And check epsilon, Q3 Q8 is the same, 6 7 1 2 4 8. After that for 5 and 9, 5 write the same, 6 1 7 4 2. For 9 we need to write Q9. Okay, and this stage is also done, and this is the new state we write here. So next for check here, Q3 we need Q2 is there, Q2. After that Q7 is there, here Q8. Next no. For here Q4 is there, yeah, need to write Q5. After that Q8 is there, no. QF, Q9 is there, QF. Next for this, what is this, Q2? For Q2 it is Q3. Next for Q3 and Q8, search E close and write the same. Okay, for Q5 and QF, for Q5, Q6, Q1, Q7, Q2, Q4, and for QF, E close of QF is QF itself. Next this stage is also completed, it is already completed. For this step we need to write here state. Next for that check NFA transition table and write this, and E close of that state. And finally we already written this, and check 561742. Here 561742 already is there, so DFA transition table is completed. And one more thing, this is the start state and final home. QF is the final state. Next last step is to write the diagram. Initially is I will write zeros only. Okay, Here is the start state. Write Q0, Q1. I will write 0, 1, 2, 4, 7. Okay. And from A and B it goes where? From A it goes to 3, 6, 7, 1, 2, 4, 8. And for B it goes to 5, 6, 1, 7, 2, 4. 5, 6, 2, 4. Next consider this 5, 6, 1, 7, 4, 2. For A it goes to 3, 6. And B it goes to 5, 6, 1, 7, 4, 2. 5, 6, 1, 7, 4, 2. And for this 3, 6, 7, 1, 2, 4, 8. A goes to, A is a self loop here. And B goes to 5, 6, 1, 7. B goes to 5, 6, 1, 7, 4, 2, 9. And next for 5, 6, 7, 1, 4, 2, 9. A goes to 3, 6, 7, 1, 2, 4, 8. 3, 6, 7, 1, 2, 4, 8. And B goes to 5, 6, 1, 7, 2, 5, 6, 1, 7, 2, 4. F. Next for 5, 6, 1, 7, 2, 4, F. A goes to 3, 6, 7, 1. And B goes to 5, 6, 7, 1, 4, 2. Okay, for like this. And the final state is this F. Okay, this is the complete solution for this. And this is the homework question in similar way, but initially AB is here. In our question AB is added here, that's all. And try to solve this. And the difference is we can see in the second step here. The start state is a 0, okay, 0 only, but we get multiple. Okay, and then write NFA transition table after that here. Okay, this is the diagram for this, and this is the solution. Check once. Okay, try. Next one is a 2B. First define alphabet string language. In the both paper they asked the same, so just look at those. And next one is a construct DFA to accept strings of zeros and ones starting with at least 2 zeros and ending with at least 2 ones. So I am starting from here Q0. I started 0, after that another 0. Okay, and it should end with 2 ones also. This is ending with 1 1 here. Fine. Then my DFA need to accept. So if initially 1 comes, I need to reject. I will introduce another state, that state. Here any number of 0 and 1. And 0, 0, 0 it should be started. And in the middle if 1 comes, I need to go that state. Okay, 0, 0 started, and after that here 0 comes in the middle. Okay, fine, any number of 0 you can loop that. And 1 goes, and after that again here 0 comes, add to here, and 1 comes, it goes like this, and here 1, and it should be ended the 1 1. So if 1 comes, that is fine, ending with 1 1 only. Next start with 0, then goes here. Okay, take example and check whether this DFA is accepting or rejecting, and you can get clear idea about this DFA. Okay, and one more thing I hope you get. Okay, start with 0 0 and ending with 1 1, and in here any number of zeros and 1. Okay, check with the rejecting strings also. So next is the 3a1, define a regular expression, refer notes and strings of A's and B's whose second symbol from the right end is A. Okay, so this is the first, second symbol is A, and in the first symbol A or B. Okay, and here any number of A's and B's can be. Okay, so from the right end the second symbol is A. In the beginning either it is A or B, and from right side the last may be any number of A's and B's. Next, obtain regular exception to accept with two or more letters but beginning and ending with the same letter. I think I did in the module 2 itself. So begin and input is A and B, right? Then begin and end with the same letter. Okay, if here case 1 is there, if it is begin with A then it should be end with A, and case 2 is if it is begin with B and end with B only itself. So for case 1, here any number of A's and B's, here also any number of A's and B. So what is the final regular expression? A plus B whole star A plus B, A plus B whole star B here. Okay. Next, fourth one, obtain NFA to accept strings of A's and B's starting with the string AB. Okay. No, starting with the string AB. No. So first Q0 A, Q1 B, Q2. So in DFA we need to write every input to each state, but there is no such condition. We should be start with AB and we can write the final one. Okay. Next, obtain NFA for regular expression A plus B whole star. In the same way they given A plus B whole star B, A plus B whole star in first paper I solved there. So check one. And this also I solved in model question paper 1. So go there. Next one is a state and prove pumping lemma, and the question is I already solved there, and I will solve in the this question in last of video, which is closure property of regular expressions. Next one is a 5-way obtain unambiguous grammar for the given grammar. Okay, they didn't say here to show the given grammar is unambiguous. Okay, they asking to write again and grammar. Okay. In module 3 basically there are three concepts: ambiguous grammar, unambiguous grammar and inherent ambiguous grammar. Okay, in ambiguous grammar type they ask the question show this is ambiguous or not, and we need to show what two different parse tree, and since the parse tree are different the given string or grammar is ambiguous. Okay, in case of inherent ambiguous I solved two questions, or they may ask the same. Okay, and in unambiguous grammar we need to know two theory. Okay, what not like a theory, it's like rules. First one is associative rule and second one is precedence rule. Okay, so this is for 5 marks. I am not going in depth of the what is associativity, what is precedence rule and all. I will explain the answer anyhow, and as much as required, not in depth. Okay, so this is a given grammar and it is a ambiguous grammar. Okay, we need to convert give an unambiguous grammar to this. Okay, so what they are saying is for this grammar obtain an unambiguous grammar, which implies that the given grammar is ambiguous. Okay, what you meant by ambiguous? There are exist two parse tree. Okay, consider this is an example, id plus id star id. Okay, this is a grammar. What is this? Ambiguous grammar. Okay, e, okay, it derives e plus e. I am trying to solve this. Okay, e plus e. Next, e gives e star e, then here it replaced by id, e also replaced by id, e also replaced by id. Okay, and another past tree is like e gives e star e, next one is e gives e plus e, id star id, next here also id. Okay, this is the two different past tree. Then what is the disadvantages of here? Okay, if consider I have two numbers 2 plus 5 into 3, you know, star is a higher precedence. First we need to solve star, then we need to solve plus. So 5 into 2 10, next 10 plus 2 is 12. This is the order, right? In this case it is going to solve the same. Okay, 5 into 2, this is the initial one, and after that it solve plus. Okay, if I consider this, then the solution like 5 plus 2 here 7, next it is multiplied by 2, which is 14. So this tree can't be possible, right? So only this is the correct solution. So we need to remove what? Ambiguity from here. Okay, so this is the rules. Okay, first one is the associative rule, which follow left to right. That means here plus have a left associative rule, and next minus, and star is a left, and division is a right associative. Next open here in the right side, closed. Next ABC means it is an identifier, that's all. Next the precedence. So plus and minus have low precedence. After that, okay, after that multiplication and division and parenthesis. The next one is identifier. Okay. In case, okay, I will tell how I get this unambiguous grammar. So this is the final solution, final unambiguous grammar. Okay. In this case, what happens, you know, here e derives e, and here also e derives e, here also e derives e. This is called left associativity. Okay, in this case we when converting into unambiguous grammar, we need to maintain it separately. So I am introducing a new variable t. Okay, after that t derives a multiplication and division. Here e gives in left side e and also right side e, right? We need to follow plus and minus in such a way it moves to left to right. So e, I am introducing t because to follow the associative rule properly. Okay, then I introduced t here, t star f, and t divides f, and f gives parenthesis e, and this is the same as it is. And why this t and f? Because it need to iterate. If here more number of 2 is added, it need to give the multiplication more times, right? So I write a t another again to get a iteration. Okay, and one more thing I said here, identifier have highest precedence and the plus and minus have lowest precedence. But here plus and minus are in the beginning. You may get a doubt why the precedence is here higher, but the rules is like that the one which is away from the starting state has the highest precedence. Okay, here A or B or C is away from the start state, so this is the highest precedence. After then this comes, and after then multiplication and division, after that plus and minus is comes. Okay, this is the general rules. And here also the tree, when we solving it goes to bottom up, and first it solve multiplication, after that it goes for plus, not like the one who begin starting. Okay, and I know it little bit confusing, and if you need more clarification, watch some other videos, okay, in the present in the YouTube. And for 5 marks this much is enough, write this much. And if you didn't understand anything related to unambiguous grammar question may arise, so write this. Okay, and after that they asking to write the expression to get to the derivation for the expression. This is nothing but just a substitution process, a plus b whole star a minus b there, and don't use this ambiguous grammar, use this unambiguous grammar. Okay, what is that? E gives a t and t gives a t star f. After that, here t itself as a f. I am substituting t by f. After that, f gives a parenthesis e gives again e plus t. So substitute everything and you will get finally a plus b whole star a minus t, and this is the answer. Okay. Next one is a 5b. For the given grammar, obtain LMD, RMD and pass tree. This is easy one. So in case of a leftmost derivation, start from the initial state and write ABB. And one more thing, you need to start from the start state only. Okay. If I need here for the, this is a given string, then they mention A, and we can't jump to A because it also producing A na. Start from start state only. Then it gives A B B, next A gives A again, then match the string and substitute to the left, from the left move like this. And for RMD, start like this. Okay, first you need to get B, next BAB right the way. So here it moves like from B, substitute here, and finally you will get AAB AB. Next pass tree using LMD or RMD, or write for the both, that's enough. Next write the push down automata for this. This I already did in module 3, right? So watch there. Next one is a construction of CFG. So next topic is 6A, construct CFG for the following language. So in model 3 beginning I solved many questions related to that, and many of these questions is already solved with the example. Now I directly write the grammar for this, and if you need explanation just check that once. Okay. 0 power 2n 1 power m where n greater than equal to 0 and n greater than equal to 0. Okay. How many zeros? First check how many zeros in the beginning. 2 zeros we need. Okay, I will write a grammar to accept 0, and here n greater than equal to 0 means it should start from epsilon, and 1 power m means it should be accept 1. Okay, 1. After that any number, and base case here also equal to 0, and the main grammar is this to combine both. Okay, 0 power 2n and 1 power m. This is the solution for first one. Next, WW reverse. So what is the W reverse of a string? If I am starting from AB, then this reverse is looks like BA, correct? Consider BBA and reverse is ABB. Okay. So what is the meaning here? If it is starting from A, it should end so A. If it is starting from B, it should end with B. Okay. That means what? So the grammar will look like S gives, okay, if it is start with A, it should end with A, and in the middle any number of A's, and after that if it is start with B, it should also end with B. Okay, and also don't miss this SS also, and base case epsilon. And why we have SS means, oh sorry, for this we, okay, it start from A, it ends with B, ends with A, and B, and if one A comes, a single A comes, that should need to accept, right? And one B, it should be accept. Okay, if the string is WC WR, in that case here base case is changed to C. Okay. Next one is at least one occurrence of 101. So one occurrence of 101, and after that, in the beginning there should be any number of zeros, okay, and there may be any number of 1 also. Base case is epsilon, and y gives also any number of zeros or any number of y, and base case is epsilon. And next one is the equal number of a's and b's. So okay, here S gives equal number of A. Consider if I have 2A, then I need to have 2B. So if I have 2B, then I need to have 2A. So S gives A, start from A, end from B, and in the middle any number of B's. And in second case it looks like B, A, and here any number of A's and B's. And here one more S is because if it is AA and here BB, to accept these conditions, okay, SS is required here. After that, what was that? Obtain a grammar to generate a language of string 0 having a substring 000. So this is nothing but this only 000. Okay. Next, convert into CNF. So CNF you need to apply the 4 simple rules, right? So I hope you will solve this. And eliminate left recursion. I don't know the left recursion topic is there in our syllabus or not. As I know, in eliminate left recursion, I think it's out of syllabus and I don't know also. Next one is a convert the above grammar to GNF. This is out of syllabus, but again they given in model paper 1 I solved one problem, and here I will solve this one, and one more question is there, convert the grammar into given grammar into GNF. So I have provided a CNF to given grammar into GNF in my Telegram channel. I will share the link. In that PDF. Both 3 problems are there. If you want, then you can get it, and you solve the another one problem. Okay. Now I will solve this. So this is the question, convert the into GNF form. So in first paper we saw that to convert to GNF, okay, first see what is Chomsky normal form. You should have either one single letter, small letter, or 2 caps letter. In a GNF, the final output should look like either one single small letter or else small letter followed by multiple capital letter. Okay, that is the difference between CNF and GNF. So in the first step we need to obtain the CNF for that. So in this question, so is there any epsilon production? No epsilon. Then is there any unit production? There is no unit production also, and it is already completely in CNF form, either one small letter or 2 capital letter. Okay. Next, step 2, we need to rename the variable, correct? So I am writing this A as A1, then B as A2, C as A3. Next, for B, what is there? Here A2, and for C it is A3. Next C means A3. Next A means A1. Next B as it is. Next A means A1. Next B means A2. I justly rename the variable. Okay. After that, check here. Here 1 and here in the beginning 2 is there. So 1 is less than 2. Leave this case, and here 2 also less than 3. Leave that case, but here 3 greater than 1, we need to substitute for A3. This is the GNF rules. Okay. Next, for A3, In the place of A1 I am substituting A2 A3 and A2 as it is, and it gives A. After that A3 multiply inside A2 A3 and A2, after that A. Next A2 gives what? This is okay. A3, and again I am substituting for A2 here, that is A3 A1 or B and A3 A2 as it is, after that A. Okay. In this case, in previous problem we don't have any left recursion case, but in the case 3 equal to 3. Okay, when I equal to j happens, then we need to apply left recursion. This is also a GNF rules. When I is greater than j, in that case we need to substitute there. Okay, so what is the meaning of left recursion and how to solve that? So here this is the left recursion rule. Light is reflecting. Okay, A gives A alpha or beta, so consider this is A. Before that, okay, before that solve this bracket, then we will get A3 A1 A3 A2 and again multiply A3 A2 inside the B, so A3 A2 B after A. Okay, then the condition is left recursion is A alpha or beta. Okay, this is the left recursion case. So in our problem it is looks like this is A and alpha, and we have two betas, that is beta 1 beta 2. So what we need to do is, this is the formula. Okay, A1 beta A1, and here A1 is a new A dash is a new variable we substituting. Okay, in that place we can substitute anything, and A gives alpha A dash epsilon. Okay, so A3 gives B A dash. So B means in our case we have two B's, betas, so write as it is first A3 A2 B and A. Okay, after that this is my A dash. Okay, Z. Then what is the A dash? This is A dash here. Okay, A dash gives alpha A dash epsilon. Then alpha is A1 A2 A3 A1 A2 A3 and again A dash, that is Z, and gives epsilon. This is left recursion. Next after solving this we get epsilon. That means we need to eliminate epsilon production, which is the step 1, right? We need to solve after this step. So okay, eliminating null production means A3. So Z is a null variable. Null variable is Z here. Okay, A3 A2 B Z and AZ as it is. After that if you substitute epsilon here, then we get what? A3 A2 and B, then if we substitute epsilon here, then it is A. Okay, then Z gives what? A1 as it is, right? And if we substitute epsilon here, it looks like A1 A3 A2. Okay, this is the removal of null production. Okay, next check for, then here it is A3 is in the form of here single terminal is acceptable. After that one terminal followed by make arrangement. Okay, one terminal small letter is followed by two caps, next here also and here also. Next A3 is okay, but what about A2 and A1? A2 and A1 still it is not converted into GNF, right? So we need to substitute. So I am taking A2 first, and in the place of A3, substitute this. Okay. So A3, A2, B, Z I multiplied with A1. Again in the place of A3, AZ multiply with A1. In the place next write A3, B, A3, A2, A1, A2 and multiply A1 to that, and after that A here multiply with the A1 and remaining is B here. Okay. Next substitution for A1. So in the place of A2, so write A2, A3, A2, B, Z, A1 and multiply with A3 here, and write the same AZ A1 multiply with A3, write the same multiply with A3, write the same multiply with A3, write the same multiply with A3. Okay. Now you can check it is in the form of one small letter and somewhere and some capital letters. Okay. There is no limit of either it have 2, 3 or any number. Next this is Z. Okay, the Z is still not come to GNF format. So here Z is there na. In the place of A1, here also A1, substitute the A1 production here. So this is B. I just arranged this. Okay, B, A3, A2, A1, A3 and write complete A1. Okay, in the place of A1 write this A1. Okay, and multiply with the A2, A3, Z. Here A2, A3, Z. Okay, next after that we have substitute A1 and write A3, AZ. Okay, next again you need to rewrite this just by multiplying inside this. Okay, multiply. So B, A3, A2, A1 and A3 again A2, A3, Z. So write the final Z here after multiplying all. This is the answer. So try to solve once. If it is not understandable, then just leave it. Okay, anyhow it is out of syllabus. So if it consists any epsilon null production, we can do step 1 and we can write the step 2 also, and from substitution okay, need to practice once. While solving this step I got to know what is left recursion. So I guess eliminate left production is need to follow these rules. Anyhow, I am leaving this, I don't know. Okay. Next, again show that CFL is not closed under union, concatenation, star and complementation. So, okay. And in module 5, already said Turing machine construction is need to study, and the construction and the table and how to write the ID, 3 cases for 12 marks. Okay, and here for 10 marks. And what is a charge Turing machine, right? And linear bound automata, explain multiple Turing machine with the neat diagram, and so many theory questions are there. And in here explain multiple Turing machine solution I given in module 1. So refer that, and for 5 marks it may. And explain such Turing machine I don't know, and here linear bound automata also. So refer something in the Google. So again come back with the closure properties of regular language, closed under union, concatenation, clean star, and extract they added intersection and difference. Okay, and they closed under again homomorphism and inner homomorphism, and so many are there. So first the union, concatenation and clean star are very important, and intersection and difference also. So okay, let's check. The theorem says what? The regular language is closed under union, concatenation and clean star, and also set difference, okay, intersection and difference also. Next, write here intersection and difference. What is the proof? We studied under conversion into epsilon NFA, convert the regular expression into epsilon NFA. In that part, I explained the three concepts. If the union comes, then we need to add with the epsilon, and if the multiplication comes, we just write a single epsilon and need to multiply the states. And for the clean star also, if r and if r is one state, then its a star represent what, we need to create a new start and final state and come back here, and from the start state and final state another epsilon connection is there. Okay, this is the problem, not a theorem, this is the rules I explained while solving epsilon NFA. Write the same and add, write the little bit explanation. So if L and M are a regular language, consider L and M are the regular language, then union also a regular language. Okay, then since L and M are regular, they have a regular expression, say L equal to LR. Okay, L is a language, and they considered R as an example, LR, and M consisting of S. Okay, and L union M means adding with the help of epsilon. It should be also a regular language by defining of the plus operator for a regular expression. So write this much. Next, for concatenation theorem, if L and M are same, right? Okay, if L and M are regular language, then concatenation also what, regular language. Then so concatenation again, L consisting of R and M consisting of S with the help of concatenation operator, that is multiplication operator, here addition operator. Then for clean star we need to write what, only L, take only L, and then so L star, that is a clean star. Since L are regular, they have a regular expression, say L star, L equal to R star by the definition of star operator here. Okay, that much only enough. And for intersection and differences, at difference, if L1 and L2 are regular, then L1 intersection L2 is regular. So L1 intersection L2 means what? Okay, L1 complement union L2 complement whole complement. It is the rule, one rule I guess in first PU it was there. When intersection comes, this is the formula. Okay, you can check also. And because why we union take, because we already know it is closed under union. Okay, and complement also, the regular language is closed under union and complement, so that's why we using this formula. And since the complement L1 and L2 complement is regular, and L1 union L2 complement is also regular, so that's why its complement is regular. So after that, set difference, if L and M are regular, there so L minus M. So proof is that let A and B be a DFA whose language are L are respectively constructed. So the product automation of A and B make final state of C public where. So I also didn't get what is this. So what the proof say, let A and B are DFA, consider it is a DFA respectively, and L and M for A, L is a language, B is a, M is a language, and construct, this is C. Okay, construct C, the product automate of A and B make the final state of C. Okay, A and B, A minus B means it is a final state of C, and C, B the pairs where A minus state is, but B is not. Okay, so write this, try to mark. The next closure property of CFL. CFL show that CFL is not closed under union, concatenation, star and complementation, But actually CFL is closed under union concatenation and star, but not in complementation. Okay, concatenation and clean star, but not under intersection and complement. So I don't know whether the question paper is wrong or this is wrong. So in actual case, the CFL, if there exist two context-free languages, say L1 and L2, consider some example, right? Okay, and the grammar is any here is A or B. Next, start with epsilon here, and S2. Consider this is S2 another, not for this language. Okay, another grammar B or A. Next, then their union is represented with this. Okay, L union, S union S2, S generated string from both of the string, then that is the union. Okay, the output of S is considering the solution of both the grammar. So L is closed under union, and for concatenation also same. Okay, but here S1 into S2, and this generates the solution of this and this also. So this is closed under concatenation, and after that clean star, again same we represent with like this. Okay, S dash which represent the clean star one, S1 generates L star producing CFL, and in case of intersection L1 intersection L2 if we take, then it is like, I will tell this here A and B and C and so but we here we have A and B and C and also I will tell with the example. Okay, so this is the example for that only. Okay, here is a union one. So there is a production which producing multiple number of A, and after that A gives a B, and another production of a grammar saying what it produces multiple B and B derives A. So S1 gives what? So after that we are union, that means adding those two production P equal to P union P1 S1 S2. So S1 means what? A or any multiple number of A's, then A gives or B, next S2 gives B, next B gives A. Okay, we just added both grammar, that's all. And so here we can see S gives A, this A generates B, we write the DF, right? First we write the production, next we concatenate it there, next with the help of DFA we are trying to understand what it is. Okay, S1 here with the help of A, it reaching a state, A gives multiple B and it reaches final state. For S2 also it produces B and reaches to B state and it gives multiple number of A's. This is the DFA for this. Okay, what happens if we concatenate it with the help of epsilon? It produces S1 also, S2 also. This is my S. If I added this, it's producing both the production. So if it is a CFL and this is a CFL, then their union is also CFL. Okay, this is trying to say what is this. Next concatenation. So same production is there, but we are applying concatenating this A, B and B also. B gives A, we just multiplied here. Okay, then we can see here when we multiplying, so S1 with the help of epsilon, and we created a new start and final state. Okay, here, okay, this is the final state of this only. Okay, we added S, next we've written the A and B with the help of epsilon, we concatenated, and the concatenated DFA will produce both of the production. So CFL is closed under concatenation also. Next one is clean closure. So again the same, but what is the closure of? Yes, we need to take S1 as S1 S, next epsilon. What is S1? We are, what is the clean closure of? Say here S1. So we are S1 and again S, that is clean closure. We are adding the star there. Okay, S, S1. So S1 gives AA and A gives B. Okay, how the clean closure in the module 3. Okay, adding a new start state and final state, and adding epsilon, the same case here. Okay, clean closure. Then whatever the output DFA have, it is the closure of S1 itself. Okay, so this clean closure also closed under CFL. So next one is for intersection. So consider A1, A and B and C M where M are n greater than equal to 1 and another language. Okay, where n greater than M and n greater than equal to 1. And for this the grammar which is looks like this, which I solved in inherent module 3. Okay, the same question I guess. So try to get a language, example language for this. Okay, in this the both the languages are look like this in ABC or AABB. Write some language for both grammars and you will get need to get the intersection of both. So in both case ABC are common. So in both cases A, B, C are the common. So we've written A power n, B power n, C power n where n greater than equal to 1. So this is the same goes here. L1 intersecting L1 is gives A and B and C n where n greater than equal to 1. But what happens? L1 intersection L2 can be defined by Turing machine or two stack push down automata. We need to define with the help of Turing machine or we require a two stack push down automata, so it can't be a CFG. Okay, so intersection is not closed under CFL. Then complementation, the formula which is the same looks like in a regular explanation closure property, right? So L1 intersecting L2 is not necessary as CFL. Try to write this example or write this theorem. Okay, both are the same anyhow. And what they asked to show not closed, they asking everything is not closed under CFL. So they may be trying to contradict the proof. So I don't know about that much also. So this is the paper. Okay, I tried my best. Hope by hoping it's helpful for you. So thanks for watching and take care. Bye bye. All the best.